What page is this on? What page is this on in the text? 372, I believe.
Or 272,
272. All right, so we're on page 272. We want to find the Cauchy bound. The Cauchy bound is just going to be all the coefficients divided by the leading coefficient. So we're going to go 1 divided by 1 and 12 divided by 1. Okay, so I take all the coefficients divided by the leading coefficient. And we make them all what? Because we want absolute values. So which one's the largest, 1 or 12? 12 is the largest, so what is the Cauchy bound?
13.
Negative 13 to what?
13.
So that means our zeros have to be between negative 13 to 13. There are going to be no zeros that lie outside of that. So every place this graph crosses the x-axis has to be between negative 13 to 13. All right, now let's go to the rational root theorem. Part B. Part B I'm going to do in red. Okay, part B, you need the P and the Q. Which one's the P, which one's the Q?
The constant is the P.
The P is the constant and the Q is the leading coefficient. So here we go, part B. I'm going to put it down here. A P is all the factors of 12, plus or minus. So what are all the factors of 12?
1,
Plus or minus 1,
2,
plus or minus 2,
3,
plus or minus 3,
4,
plus or minus 4,
6,
plus or minus 6,
12.
plus or minus 12. The Q is just plus or minus what?
1.
So what's the P over Q's?
All just the P's.
It just ends up on being all the P's, right? Does everybody agree?
Yep.
Because if I take all of these P's and divide them by 1, you're just going to get the same thing. So there's no additional ones. So it's plus, there's no fractions this time. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12 is all the P over Q's. That's your rational root theorem. Those are all the possible rational real solutions. Okay? So it wants us to graph. We're going to skip that. We're going to go right to D. I'll do D in green. We want to find all the zeros. All right, we got to start trying stuff. All right, here we go. We're going to have the box. So what should we start with, everybody?
1.
All right, guys, you try positive 1. Girls, you try negative 1 this time. Guys, you try positive 1. Girls, you try negative 1. Boys are going positive 1, girls are going negative 1. And then if that doesn't work, boys go to positive 2, girls go to negative 2. Tell me when you find one that works. I'll send you the early out schedule. On Remind. How's that sound?
Good.
Morris, bingo. We got one.
Which one works?
3.
3 works. Everybody go to 3. All right, right now draw a box. Let's put 3 in the box. Here we go. Here's the coefficients you should have put down. You should have put a 1, a 0, a 1, a 0, and a negative 12. Please say you did zeros.
Yeah, I don't think it's 3 then. Forgot 0.
Seriously?
We did not.
Well then, how did
Oh
you?
my God.
Oh my gosh. We can't rely on the guys, can we? Hold on, it might still work. Let's see, because the zeros are in a place where it might still work. Let's go 1. We get a 3. We get a 3. That gives us a 9. That gives us a 10. That gives us a 30. That gives us a 30. That gives us a 90. Guess what, guys? Those zeros matter. All right. 1 doesn't work.
Negative 1 doesn't.
Well, I would know
Negative
the regular
1.
one
Let's try 2.
because
You guys have not practiced your homework.
practicing.
What did you do yesterday? All of them wrong?
No, I actually went to church.
No, yesterday in class when I was gone.
I had my MCA.
Oh, yeah. You'd be lucky that I did that for you.
Yeah, I would
two
be
doesn't
cooked.
2 doesn't work?
Dude, everything was lined up.
All right, go to 4. Go to 4 and negative 4. Keep going until we find something.
Okay, guys, do you know what you're doing now?
Yeah, we got it now.
Did you guys do 3?
Everybody's
I'm trying. I don't think negative 6 works either.
Okay, go to 6.
I don't think any of them
Oh, they work. There's 1.
love with the actual.
But it gets like bigger and bigger, and then I'm like, that doesn't add up. You know what I mean?
Keep trying.
won. Keep trying.
Like negative 3 didn't work, right?
Oh my goodness.
Alright, let's try. Maybe you could try it again.
Did you do 3 yet?
Yeah, I don't think 6 works either.
Did 12 or negative 12 work?
I haven't tried that yet.
12, it's got the 12.
Did 6 work?
You try 6, I'll try 12.
It's the new cusp. None of these work.
Okay, this one's just gonna be huge.
All right.
Yeah, that ain't working.
All right, let's talk about it now. Okay, so nothing's working. Watch this when I graph it.
No solution.
No, there's a solution. When I graph this, it clearly crosses the x-axis,
We
but
don't
I'm not
see it.
finding it. Can you see it now?
Mm-hmm.
It clearly crosses the x-axis though. And it looks like it's between negative 13 and 13. So why am I not finding anything? We have tried everything on our list. This is called the rational root theorem. Rational.
It isn't rational.
It's not rational, it's irrational. So that means nothing plus or minus 1 didn't work, plus or minus 2 didn't work, plus or minus 3 didn't work, plus or minus 4 didn't work, plus or minus 6 didn't work, plus or minus 12 didn't work. There's no rational solutions to this. So either this factors or you would have to use a what? Talk to me here. Either it factors, because synthetic division doesn't work. Either it factors or you would have to use what? Maybe, I don't know if you can use quadratic formula. You would need the calculator.
Oh, let's go.
Okay? Now, your good news, it factors. Because I'm not going to give you one that you need the calculator for. But I'm going to show you real quick how you can check it with the calculator, where if you get stuck and where you're on your homework and if you're spending so much time trying to find them, there is a shortcut. But if you don't have the calculator, there's no shortcut.
No wonder.
Okay? What you could do is just go to your calculator. Everybody graph it. Go x to the 4th plus x minus 12. X to the 4th plus x squared minus 12. You need to do this with me. Okay? Go to your
Are
calculator.
we at y? 1.
Is there an extra calculator? Throw her that extra calculator. So she doesn't have to walk over there.
Plus what?
X to the 4th plus x squared minus 12. Hit zoom 6 because zoom 6 resets your window. Graph it.
There's something wrong with this one.
It's called the user. You're either a slow driver or a fast driver.
Do we do trace
There we go,
now?
I fixed it.
Okay, you're a good driver. Okay. X to the 4th plus x squared minus 12. Has everybody got that typed in? Press graph. Hit zoom 6. You can see it. Can I see where it crosses the x-axis?
Yep.
All right, let's review how to find those. Does anybody remember how do you find where it crosses the x-axis?
You moved the thingy.
You got to go second trace. And what option do you use to find the x-intercepts, the zeros?
The 0.
Zeros, duh. Okay, zeros.
Mine
And-
jumps over though.
all right. It's fine if it jumps over it because here's what it asks you. It asks you for a left boundary, does it not?
Yeah.
Put it to the left of where you think it crosses. Now, is that going to be above or below? Depending on which one you do, if I do the one on the right, the left bound is going to be what? Everybody look at me. You got to be where I am. You can't do your own thing. Okay? Did you go second trace 0?
Yeah.
Is it say at the bottom of the screen left bound?
Yeah.
you got to use the left and right arrow key and put the little itsy bitsy spider a little bit to the left of where you think it crosses the x-axis, which this time is going to be below. Hit enter. Now it's going to ask you what?
Right bound.
Right bound. Now put the itsy bitsy spider a little bit above the x-axis because you got to be to the right of where you think it crosses. Hit enter. Yours asks a third question. What does it say?
Yes.
Just hit enter the third time. On the guess, all you got to do is hit enter.
Mine said error.
Then you didn't do it right. Second trace 0. Follow me.
That's what I did.
Okay? You didn't go to the left. Which one are you doing? Which one are you doing? Are you doing the one over here or the one over here?
Oh.
Because if you're doing the one over here, it's going to be different. If you're doing the one over here, a little bit to the left is going to be below, a little bit to the right is going to be above. A little bit to the left is going to be below.
Okay, I got it.
A little bit to the right is going to be above, and then hit guess, and you're going to get 1.73. I know what 1.73 happens to be. It's root 3. I'll tell you why in a second. Okay? I haven't memorized. I had to memorize it in grade school. Here we go. Second trace. You did. You had to memorize square roots back in the day before they had scientific calculators. You had to memorize all the way up to root 10.
It's just a negative.
All right, now, second,
You should tell us what they are.
Square root of 2 is 1.41. Square root of 3 is 1.73. Square root of 5 is 2.21. And then I forgot the rest because I don't need them anymore because I never use them. Because I got graphing calculators now. All right, go to 0. I used to have them all memorized up to 10. I got square root of 9 memorized. That's 3. And square root of 4 memorized. That's 2.
I have those ones memorized.
Okay, good. And square root of 1 is 1. All right, now, go to the left one. Hit second trace 0 again. Now, this time, the left bound is going to be where?
Above.
It's going to be above. The left boundary will be a little bit above. Do you see the difference on the other side? A little bit to the left will be above. A little bit to the right would be where?
Below.
Below. And then do your guess. And then it's negative 1.73. You got it? Now, that means it's irrational. It's a decimal that I don't know. I do know. It's going to be root 3. Now, watch this. Go back to the original equation. Synthetic division did not work. Everybody agree?
Mm-hmm.
Let's try to see if it factors. Set it equal to 0. All right, get your factor cheat sheet out. Is there a GCF? Can I take something out of all of them?
No.
Is it a binomial, a trinomial, or 4 or more?
4 or more.
Try.
Oh, sorry. I was looking at the power.
Yep, the power is 4, but how many terms does it have?
Oh, 3. It's a try.
All right, it's trinomial. Does it fit the pattern of power, half the power, constant? Does it fit the pattern of power,
Yes.
half the power, constant? So as long as it fits the pattern of power, half the power, constant, you can factor it with the Knudsen method. But this doesn't even need slide and glide, does it? So when you split x to the 4th, do you get x and x, or do you get something else?
X squared.
You get x squared and x squared. And then you do Knudsen method, and you need to find the factors of negative 12 that add up to give you 1. What are the factors of negative 12? Negative 12.
4.
What kind of 4?
Positive.
Positive 4 and what? There we go. It factored. Does everybody agree? Make sure you can factor, or you're screwed on this test. Does everybody see? It's x squared plus 4 factors of negative 12 that add up to give me a positive 1. That'd be a positive 4 and a negative 3. Does that add up to give you positive 1?
Yes.
Yes. All right, now, can I set each one of these equal to 0 since they're x squareds?
Yes.
Yeah. So if I set this one equal to 0, I'm going to get x squared equals negative 4. What's the square root of both sides going to give you?
2.
Plus or minus what? 2i. Boop. Poke the I out. Negative underneath the square, it gives an imaginary number. So 2 of the solutions are imaginary. And then we're going to get x squared minus 3 equals 0. What do we get?
Plus or minus square.
Oh, Mr. Morris was right. Plus or minus root 3? I believe plus or minus root 3 is 1.73 and negative 1.73. Now, why did it only cross the x-axis twice and not 4 times? Because 2 of the solutions are what?
Negative or imaginary.
Imaginary. That's why you only saw it cross twice. Okay, today, we got 8 minutes. Descartes' rule of signs.
We've done this before.
All right. Descartes' rule of signs. Last thing from 3.3. And then we get back next week. I'll do 3.4, and then we'll just test on when we feel comfortable to test, and then we'll go into chapter 4. All right, Descartes' rule of signs. Suppose f of x is the formula for a polynomial function written descending orders of x. Okay, got 8 minutes. This is not super hard. Descartes' rule of sign. This is the third and final method. We have Cauchy bound, we have rational net theorem, and now we have Descartes' rule of sign. Let P, capital P, denote the number of sign Now this makes sense when I use P and N, what I'm about to use, because capital P is going to represent positive. Everybody, what's capital P represent? Positive. For Descartes' rule of sign, capital P is positive. So it says, let capital P denote the number of variations of signs in the formula f of x. So you're going to take your original polynomial in descending order, and you're going to see how many times it switches signs in the terms. Okay, you're just going to count the number of sign variations. All right. Then the number of positive real zeros, counting multiplicity, is one of the following numbers. It could be whatever P is, which is going to be the number of sign variations. So let's say we get the number of sign variations. Let's say we say it changes 3 times. Let's say we say there's 3 sign changes. Then here's the number of positive real zeros that are possibilities. 3, then it would be 3 minus 2, which is 1. And then you go until you can't go any further, because once you get to 0, you stop. So it'd just be 3 and 1. Okay, and when we do an example, it'll make sense here in a second. Okay, let n denote the number of variations of signs in the formula f of negative x. So to do the negative one, you have to plug negative x in and see how many sign variations there are. Let's say that Brody figures out there's five sign variations. Then what he's going to do is then the number of negative real zeros, counting multiplicity, is one of the numbers. It could be 5, 3, 1, and then we would stop because you don't go past 0. Okay? And then I'm going to explain how to summarize it. So let's look at an example. A few remarks, and then I'll go through it because it'll make sense when I actually do an example. To use Descartes' rule of signs, we need to understand what it's meant by a variation of sign. So let me explain the variation of sign, because that's the first question that probably Morgan's going to ask. She's going to be like, I don't know what you're talking about with variation of sign. All right, okay, Morgan, here we go. We got a polynomial. 2x to the fourth plus 4x to the third minus x squared minus 6x minus 3. You're literally going to count how many times it changes signs. Does it change signs from here to here? No. Positive to positive does not change sign. Positive 2, positive 4. Does it change signs from here to here? That is a sign variation. That's 1. Does it change signs from here to here? Does it change signs from here to here? So there would be only one positive sign variation. So that means there's only one positive possible positive real zero. Gets to be a tongue full. Okay, so we're only going to focus on the sign of the coefficients. Start with a positive, followed by another positive. Then if it switches to a negative and stays negative for the remaining 2 coefficients. So there was only one sign variation. So since the signs of the coefficients switch once, read from left to right, we say f of x has one sign variation. We assume that f of x is written descending order and concern ourselves with no non-zero. So if there is a missing term, you don't worry about it. Okay? You don't worry about if x a third is missing. You don't care. All right? Second, unlike rational zeros theorem, Descartes' rule of sign gives us an estimate of the number of positive and negative real zeros, not the actual number of zeros. So Descartes' rule of sign does count multiplicities. For example, if one of the zeros has multiplicity 2, Descartes' rule of signs would count this as 2 zeros. So if x equals 1 has multiplicity 2, Descartes' rule of signs counts that as 2 zeros. It's just 1 shows up twice. And we know what happens when it shows up twice. It does what on the graph? Bounces. All right. Notice that the number of positive or negative real zeros always starts with the number of sign changes and decreases by an even number. So if you have 5 sign variations, what you're going to end up with is 5, 3, and 1. If you have 6 sign variations, you'd have 6, 4, 2, and 0. You don't go past 0. So you keep subtracting 2 until you can't go any further. And you stop at 0. So if you have 7 sign variations, you could have 7, 5, 3, or 1. You can't subtract 2 again, because if you subtract 2, you'll go negative. So you go down till 0 and you stop, okay? So if it has 7 sign changes, 7, 5, 3, 1 positive real zeros. This implies that the graph of y equals f of x crosses the positive x-axis at least once. That means you would have at least 1 0. F of negative x results in 4 sign changes, counting multiplicities 4, 2, or 0. Hence, it is possible that it could cross 4 times, 2 times, and it may not cross the x-axis at all. All right, very quickly, let's just look at one. So first of all, you do p. P is just taking f of x and counting sign variation. So the bell might ring, just stay with me. Let's see, is there a sign variation?
No.
No. Is there a sign variation? So far, 1. Is there a sign variation? No. Is there a sign variation?
No.
So P is 1, so that means there's only one positive real 0. And it's possible. It's possible. There's one possible positive real 0. Actually, since it's 1, there has to be 1, because there can't be 0. So there's one positive real 0. Now let's do f of negative x for n. So all that Brody's got to do now is he's got to plug negative x in and see what the sign variations are going to be. So it's going to be 2x negative x to the 4th plus 4 negative x to the 3rd. So for the negative one, you have to plug negative x in. Minus negative x squared minus 6 times negative x minus 3. All right, what's going to happen when you take negative x to the 4th power?
It's gonna be positive.
Stays positive. That one stays positive. What happens when you take negative x to the 3rd power?
Negative.
That one goes negative. What happens when you take negative x to the 2nd power?
Positive.
But there's a negative there already, so it's going to stay negative x squared. What happens when you take a negative x times a negative 6?
Negative.
Yep, plus 6x and then minus 3. All right, count the sign changes. How many so far?
0.
It's a positive to a what? Is there a sign change?
Oh, yeah.
Yep. Is there a sign change?
No.
Is there a sign change?
Yeah.
Is there a sign change? How many sign changes are there? So n is 3. So you could have 3 or 1 possible negative real zeros. Now, real quick, there's a summary of this. What power is this to?
4.
So here's what you can do. You can summarize now with P and N, and then what you call imaginary solutions, because it has to add up to give you 4. So here's what I tell kids to do. They do a P, an N, and an I for imaginary. So here's what they do. So there is only one positive real 0. That's definitive. There's one, no matter what. But how many negative real zeros possibilities do you have?
3.
So you could have 1 and 1 and 1 and what?
3.
Do you see that?
Yeah.
Now, this has to add up to 4. Does this one add up to 4?
Yeah.
That means no imaginary. But does this one add up to 4?
No.
So how many imaginary would there have to be to account for it? There you go. So now you get a summary. Descartes' rule of sign gives you a summary of what could happen.
I remember doing this.
Yes, you did it in pre-calc. If you took pre-calc, you did Descartes' rule of signs. Algebra 3, you might not
I
have.
remember this.
All right, see you later. I will give you some book work over break.